Before we focus into reflection and refraction of light, little bit of background. Historically, if you see, then lot of effort was made to understand light. Newton first came out with what is called as the corpuscular theory of light, that says that light is made of particles. Right? That was long time back. Now after that theory, so many things were observed, and if I can just take two names, interference effect and diffraction effect. These two effects, interference and diffraction, are such effects that they can only be shown by waves. Right? For example, in case of sound, there is interference taking place in sound. Interference means suddenly loudness or intensity increase, and at some point tremendous decrease in intensity, up-down behavior of intensity. That's interference. Diffraction has to do with, in case of light, some bending effect. Now, these two points that I'm talking about, interference and diffraction, they are exclusive to the wave. So when these things were observed, then it was thought that light was wave. Then Einstein came up with the photoelectric effect experiment, for which he got Nobel Prize. And that experiment could only be explained if you considered light as made of particles. Otherwise, you can't explain photoelectric effect. Well, then after that, and also some other work that Planck did before Einstein. Now, after all these things, one has to accept interference, one has to accept diffraction, one has to accept the photoelectric effect. And therefore, it was accepted eventually that light has double behavior. Sometimes you have to consider the wave behavior of light, and sometimes you have to consider the particle behavior of light. So that's the background. As far as our scope is concerned, which is about reflection and refraction, we don't need to get into either of these two things. I mean, no need to worry about light made of photons. Photons are the particles of light, or no need to worry about the wave behavior of light, like talking about frequency, wavelength, time period, etc. Our scope can be handled without getting into all those things. We will be talking about primarily reflection and refraction, and that can be handled by just considering rays. So we also call this discussion as part of ray optics. When some light ray or light beam falls on some object, then three things happen. One is that that object bounces back some light. Now that light, if your eyes are able to catch, then you will be able to see that object. If your eyes don't catch them, but somebody else's eyes catch those rays, then that person will be able to see that object. Or that object cannot be seen if those rays are not caught by the eyes. So one is the bouncing back effect. Second one is the transmission effect. Light enters, penetrates, travels inside, like torch light you incident in some swimming pool. That is the refraction or transmission. Third thing is the absorption. So while pink color rose looks pink because it only bounces back pink. All other colors it just takes within itself without letting them go out. And if they are not coming towards you, you don't see them. So these are the three things when the light ray hits some object. Now why does the light ray come? Because of some source. So normally there will be some source. So when it is dark, then you can't see some object. The reason for that is that rays first should hit the object and then they bounce back and reach your eyes. If it is dark, there are no rays, then where does the question of hitting and bouncing back arises? So we normally talk about some source. It could be the sun, it could be some artificial source of light. Source of light can have several components present in it, like we talk about different colors. So light is a general term. There can be several pieces, if you like, several types, if you like, which could be present. So when we talk about sunlight, then you must have heard about that prism experiment. A prism breaks down sunlight into several pieces, several colors. But that may not happen in all types of sources of light. So source of light is important. Sunlight has those components, different colors, but that's not necessary that under your street light you will find so many colors present. So source is, it depends on the source, what types of components of light would be present. Now, I don't think we'll be getting too much into these things. Let's see what comes later on. But at this point, when we talk about reflection, then we don't have to talk about different components of light. Just think of a ray, and that ray travels, and the simplest case possibly is of plane mirror. And I'm considering the nice reflecting side because depending on the surfaces, how much reflection will take place, how much refraction would take place, how much absorption would take place. These things depend. Some surfaces are very good for reflection purpose. Some surfaces are very good for absorption purpose, or some surfaces are very good for transmission or refraction purpose. So let's consider a good, nice reflecting surface. Now it's a straight plane surface. Light ray incident on it bounces back, and when it bounces back, then certain laws are obeyed. These are the laws of reflection. In fact, when I talk about laws of reflection, I don't necessarily need to state that it has to be a plane surface. They work for curved surface also. But in the beginning, let's not make things too complicated. Incident ray, the ray which reflected ray, and this is the normal to the surface. They are all in the same plane. Line number 1, line number 2, line number 3. They lie on the same plane, right? That's the rule. And this angle is equal to that angle. I hope you understand what's the meaning of 3 lines lying on one plane. On your table you can draw 3 lines, but you don't necessarily have to do that. On your table you can draw 2 lines and maybe 1 line you can draw below. So don't take it for granted that this is so obvious. 3 lines don't have to be on the same plane. So but in this case, according to the law, these 3 must be on the same plane. The incident ray, the reflected ray, and the normal to the surface, right? And then this angle is called angle of incidence, this is called the angle of reflection, and these 2 are equal, right? So these are the laws of reflection. Normally we denote angle of incidence as I, angle of reflection as R. So angle I is equal to angle R. Now, when you are talking about the image formed, you see yourself, like suppose daily, using some mirror of this type, which is called the plane mirror, and you see yourself behind the mirror. You see yourself behind the mirror. So image is behind the mirror. In fact, behind the mirror is a region that you can't see. Isn't it interesting? This is some mirror, and you are here. Imagine this mirror to be really big. What is kept behind that mirror you can't see from here. You know that, right? Behind that mirror, what is kept you can't see from here. But you see yourself behind the mirror. That's the interesting part of it. So when you are here, you see yourself somewhere here. But in reality, perhaps here something else is kept, but you see yourself here. And actually you are here. So it is your image which is getting formed, and it is not real. It is not real. Really something else is kept here. Your image is not real. It is virtual. We call this type of image where light rays just cannot go. Now why light rays cannot go? I'm assuming pure reflection. I'm assuming pure reflection. So just ignore refraction, ignore absorption also, if you like. Absorption is not really a problem here, but ignoring refraction, let's say. So no question of any ray reaching there from this direction, right? But you are seeing yourself here, and no ray is reaching there, right? I'm ignoring, when I talk about no ray reaching there, maybe there's a light source here, and that light source is sending rays. I'm not talking about those rays. This is the object. You are the object. Ray which is coming from the particles of the body, those rays are not reaching here. So still you are seeing yourself here. So that's not a real rays which are there. They are not real rays which are there. It appears that you are here, but actually you are here. So when light rays actually don't exist, but still you can see things, then it is called the virtual thing. Virtual image is what you get here. Virtual object is also possible, but this case is of virtual image. How does one get the location of image? Now before I discuss that, any questions up to this point? Let me know. Just go ahead.
Sir, you said there's something called virtual object. Could you explain what that is?
Virtual object is this type of object. I somehow think your question is not, it has not come at appropriate time, because we haven't even talked of virtual image. So first you understand virtual image, then you understand virtual object. When you have rays but I will try to explain nevertheless. Real object means what? Rays actually come out from the object. Now when I say rays actually come out of the object may not be a source of light. You don't generate light from your own body, but you may be under some source of light. So when the source of light sends rays and your body bounces them off, you become an object. So object is something from which light rays go out. Real object, like this. That's a real object. Virtual object would mean something opposite. It would, the rays would appear to meet from at that location. Rays would appear to meet at that location. That would be a virtual object. Now, talking about how to get the location of the image, I think we go for a simple diagram. So just consider this line, which is actually a plane, and now you have some object. Now object does not have to be a point. Object does not have to be a point. It can be a line, it can be a three-dimensional object. But when you treat point by point, things become really easy. Point by point. Consider a point object. Consider one ray. Apply law of reflection. Right? This is a ray. Take one more ray, whatever ray you want. Generally, straight ray is very easy, because straight ray makes zero angle with the normal, so it will come out making zero angle with normal as well. I equal to R. Straight ray. That's normally enough, two rays. Now, no question of these rays going to that side. So, appear, they should appear to be meeting, appear. Extend this line, extend that line. And let's make this dashed, and let's make that dashed also. Now they appear to be meeting here. If your eyes are here, your eyes would see that these rays are coming from here. So your brain will form an image of this thing here. Right? So the rule is very simple. And you know it every day when you see your mirror. Your face appears to be at the same distance from this point. Your face appears to be at the same distance behind this as your face is in front. This is equal to that. You also know that your face does not look bigger, does not look smaller. You look exactly, almost exactly, if I may add, as you are. That's the property of plane mirror. On the other hand, if you look at the rear view mirror of a four-wheeler or a two-wheeler, then you find, well, something is wrong. The person behind such a big car behind you is looking so small. So there you know that something is wrong in the rear view mirror of a vehicle. But here, in case of plane mirror, everything looks just perfect. So in case of plane mirror, the image is virtual. Rays are appearing to come from here if your eyes are here. Eyes must catch these rays. This ray, that ray. Normally in textbooks, you don't often see more than two rays, but that does not mean that there are only two rays. There are infinite rays. A third ray, fourth ray, fifth ray, sixth ray. There is no end to it. There is no end to it. But we don't need to show so many rays because it's enough to deal with two rays. So that's why it's a very common practice that you see in textbooks only two rays are shown. So you will say that image is virtual, image is just like the object, upright, same size. So that's about plane mirror. So the simple rule is that if there is a point here, then its image will be formed exactly at the same distance behind. Exactly at the same distance behind. Right? That's about plane mirror. Now if you have any question up to this point, then let me know. Now think about this interesting but common problem. Suppose you have two plane mirrors kept at 90 degrees from each other. And this is the reflecting surface, this is the reflecting surface. The object is here. Now I don't need to show this part, but ignore it. Ignore this part, ignore this part. Mirror is from here to here, mirror is from here to here. How many images will you get? And if you like, use the whiteboard and show their locations. Note that it's not that easy. You may have to think twice. You need to explain the answer, whatever answer you are getting. Now looking at your drawing, you are right about this. This is one answer. And likewise, this will get you another answer. Now two are okay. What about any other answer possible? Okay, I don't see any other convincing answers, but these two are okay. So it is about double reflection, like you showed this one. Won't it hit here and bounce further? Double reflection. So single reflections will give you these two images, I1 and I2. And double reflection will give you one more image, and there's a simple way to find that image. This image is formed by reflection of this on this. This image works as object for this mirror, and this image forms I3 here. So I3 is the image of I1 for this mirror. Now I2 is image for this mirror. It acts as object for this mirror, and it forms another image here which superimposes with this image. Why it superimposes can be seen from drawing. So actually you get three. Now if you are wondering that mirror is so small, then how can this image act as an object for this? Well, if the mirror is here and if the object is here, no problem, you will get image. Why won't you get image? There are millions of rays. So how about all these rays? They will all be reflected, isn't it? All of these. So even though object looks somewhat further, image is still formed. So if you have this type of mirror and this type of object, then the image will be here. Rule is the same. Whether object is within this length in this region or object is beyond. Let me know if there is any other question. Let's move on to spherical mirrors. The laws of reflection work whether the surface is plane or curved. Now, if we take such type of surface, then the laws will still hold good. So imagine this to be part of a circle. Maybe you can consider a ball, hollow glass ball, and that hollow glass ball is cut and you are able to get this piece, and then you choose to have one side as your reflecting side, and then your object is here. Just follow the same rule. Take any two rays, or even more if you like. Take any two rays or more if you like, and draw some normal at that point. Now in case of plane mirror, it's easy to draw normal. But in case of circle also it is easy to draw normal. Circle has a property, right, so that radius is always a normal. Radius is always a normal. At this point, what is the normal? Radius. At this point, what is the normal? Radius. At this point, what is normal? Radius. Tangent and normal are always perpendicular to each other. So at this point, tangent is this. At this point, tangent is this. At this point, tangent will be that. So if you are considering this ray, then maybe at this point you can imagine some tangent which will be like a plane mirror sort of thing. And the radius is very easy to construct. You should be knowing the center. You should be knowing the center. Center is called C. Center is the same center of the hollow shell from where you have cut this thing. So you have a hollow shell, spherical shell, whose center is this center. You cut this from that shell, and then you got this. So this center you already know. So join this center to that point. This is normal. This is the normal at that point. Normal, incident ray, reflected ray are in the same plane. This angle is equal to that angle. Right? So you got one reflected ray. One reflected ray you already got. Okay? And likewise, one more you can take. I think it's very convenient to take the straight one, or this one is very convenient. This one will be very convenient. The one which goes like this. And at this point, if you draw the normal, it will be this only. So this point will be very convenient. That means reflected ray would be like this. Like this. This angle will be equal to this angle. So just using the geometry, these laws, you are able to get image of any point, any object you take, you are able to get its image. And if you talk about a bigger object is made of points. You will go point by point by point, and you will be able to get image of all points. So whether you have plane or curve, those laws solve all problems. Here in this particular drawing, you can see it's different from plane mirror. The reflected rays are actually meeting each other. This one is reflected, this one is reflected. They are actually meeting each other. Actually. That means it has to be a real. It has to be a real image. Now likewise for the reflecting surface which is convex. Now by the way, this is called concave surface. So this type of mirror is called concave mirror. This is called the pole. This is called the axis. Axis, pole, C is the center of curvature, and then this length, that is called aperture, from this point to this point. It's like a chord of a circle, if you like, and that is called aperture. If aperture is big, one can catch more light. If aperture is big, one can catch more light. If aperture is small, one catches less light. The topic that we are discussing within our scope, we are discussing small aperture cases. And one more thing, small aperture cases and rays which are not very far from the axis. Rays which are not very far from the axis. These are the two things for which our results and discussions mostly would be valid. Would you like to try for convex surface? I will give you the point. This is a reflecting surface, this side, and this is the point of interest, object that is. Take center of curvature somewhere here. That will be very useful to draw the normal. Okay, you can start here if you like. Yes, that's very convenient, this one. So that's done. One more. Okay, if you are taking parallel here, that's correct. That's the normal. That's also right. Okay, looks like you already got it, nearly. So maybe you can show the location of image once rays are done. Yes. Yes, I think that's correct. So we have one reflected ray here that had to be extended because reflected rays have no intention of cutting. This one and this one. So extended back, extended back. This is correct for this drawing. So it is going to be, in this particular case, a virtual image. Virtual image. Often the non-reflecting side is shown by this type of thing, right? throughout. Now, just following these two laws, no matter where object is given to you, you can tell the position of image, no matter where the object is, and no matter which type of mirror it is, concave or this one convex. However, there are some standard cases which are very important. But before we talk about those cases, it's very important to define the focal point. Focal point. If you talk about concave mirrors, then it is found that parallel rays meet at a point parallel rays meet at a point. And that point is called the focal point. Imagine so much of energy is focusing at this point, like concentrating sun rays and burning something here. That is called the focal point. Now, if you are wondering how does one get parallel rays, parallel lines, as you learn from mathematics, parallel lines can be said to be meeting at infinity. Just apply the opposite rule of that. At infinity, take some point. The rays coming out from that can be considered as parallel rays. Like for us, sun is so far, so the rays that come from the sun, they can be considered as parallel rays. Now, that's the definition of focus, and this length is called the focal length, from pole to F, focal length. And when we talk about the convex mirror, in that case, things are different. For convex mirror would like to diverge the rays, This fellow is trying to converge the rays, and that fellow is trying to diverge the rays. So, if you take this ray, for example, it would try to throw it away, and likewise you can take so many rays. This one, like this. When you now they have no intention of meeting each other, so you extend them, and you find that they meet at some point, and that point is called focus. That point is called focus. And this is called, from here to here, from pole to F, TF is called the focal length. Now sometimes the length word can be confusing because we use sign convention. Like coordinate geometry, we use sign convention. Right side is positive, left side is negative, up positive, down negative. So length word actually here can be negative also. Now if I take this as my origin, right side as plus x, left side minus x, up plus y, down minus y. then for this case I will get positive. But in this case, if I take this origin plus x plus y minus y, then this I will get negative. So this XY system is very much used. Why is it used? Because results that you will see later on, they are derived following this convention. The results are derived that way. That's why we have to follow this. So it is we who are choosing to derive results by following certain things, plus minus sign. And therefore, when we are using those results, we have to follow those signs, because otherwise those results won't work. For assignment, I am giving you a very simple question. When we said that this thing is cut from a spherical shell and that center was C, then from P to C, this is called the radius or radius of curvature, right? So from P to C it is radius of curvature. My question is, for a plane mirror, what is the radius of curvature? For plane mirror, what can be taken as radius of curvature? We stop at this point.